Of our program. So today I would like to discuss a little bit about some elements of the thermodynamics of climate, and in fact I changed a bit the presentation after Sean's presentation this morning, because I think it's a good idea to try to make them a little, the various contributions talk to each other. So I have shuffled taken out some material that I would like maybe to discuss later in the program. And now also because some of the people in the room, of course, are not so familiar with somehow what is climate, what is a climate model, and in view of the discussion tomorrow, I want to put something on the table. So it's going to be for some more expert, maybe not so not so challenging, let's say, but I wanted to also use some terminology, and also talk about a bit about complexity, in fact. So I want to start with this, which is I've been working in my life between mostly climate physics and more recently mathematics, and I just wanted to collect here some sentences and things I have heard from mostly very, very distinguished colleagues. So we start from the first, some colleague, a very, very famous theoretical physicist, will tell me, well, what's climate? It's just a solved problem. You have some equations, whatever. And very important climate scientist who leads a very prominent institute at world level recently not only told me, wrote me an email, wrote in a text, who cares about the mathematical, physical consistency of models, better computers, better simulations, and that's it. And of course, this creates some problems. And what is the science of this? If we make this statement, it's problematic. And this is a wonderful masterpiece that I will always conserve until I have memory of it. This was a letter I received from Physical Review a few years back, who wrote, I regret to inform the author that geophysical problems related to climate have little interest for the physical community. So I tried to make the point that there was at least a problem in terms of really meaning of the word. In this statement was illogic, but it was hard. But that was interesting. And again, going to many conferences, and some of the people in the room can confirm this. We have an endless discussion, and many people who are prominent in geosciences will tell you, who cares about energy and entropy? Anyway, we're interested in temperature, pressure, precipitation. That's it. Okay, so there is clearly a lot of distances and a lot of challenges and a lot of opportunities. So
references.
Huh?
You forgot the references.
For one, no. It's that's in a private set. Anyway, regarding so let's talk a bit this word today has appeared today, complex system or complexity, and I just wanted to put a few again, just to try to give my little view on this. So somehow when we talk about a complex system, is something where more is different. That is, if we put together many parts, which we can somehow define as elementary parts, well, we have emergent properties, or we have properties of the extensive system, which are are hard to predict from the properties of the individual elements. And the critical problem is that our method for studying most of scientific problems, this is a reductionistic approach, doesn't work really, or we have to really work a lot. Another problem in many complex systems is that not necessarily you can repeat experiments. So this creates huge issues in the definition of what is a theory. We assume always that we are always able to do interplay of experiment, observations, theorem, back and forth. But if we talk about something like climate, immediately this is impossible, because unfortunately we cannot go back in time. And so there are just listed here some properties that we find sometimes in complex systems: pattern formation, symmetry break and instabilities, irreversibility with entropy production. We have sensitive dependence on initial conditions and non-trivial numerical models related to the fact that the problem is stiff. And another confusion sometimes one finds is between complicated and complex. So sometimes when I mean, a classical example of something which is not complicated, not complex, is a harmonic oscillator, something which is complicated, not complex, is in fact a gas of phonons, which you can reduce to a collection of these and by a simple diagonalization. And of course, an integrable system is not complex. And instead, we can have complex but not complicated, like Lorentz 63, which has just 3 degrees of freedom. And then, of course, if we go to turbulent fluid, they are both complex and complicated. And it's interesting to look a little bit at the etymology of the problem, which is actually pretty funny. Complex has to do with something that it's entwined and cannot be, let's say, cannot be made simple without destroying the structure, and complicated comes from folding, so it can be unfolded again. So this is you can find on internet, if you look at play a little bit with complexity, you find the conceptual maps of complexity. So these are, I don't know, they have some interest. At least people basically put discipline or concept and trying to construct a graph of cultural, if you want, or scientific influences. And I see this as an example. And so here as an example, we have something like cybernetics, artificial intelligence, and we have a various line here. We have dynamical system theory, fractal geometry, chaos theory. Then we have various aspects related to, of course, social sciences as well, and science of networks, and so on. Interestingly, just look at this map, and you see that there is a big hole here, right? Okay, and in fact, somehow what is missing is exactly this. So interestingly, there are lots of elements here that were born or are closely related to geophysical problems, and there is not, there is the elephant in the room. There is nothing here which talks about, say, climate, or by climate in this case, I mean also meteorology. This doesn't exist. So this field is not perceived as being part of this story for the good or the bad, but I think it's related to the problem that it's often hard to see how we define the leading problems in climate science, and somehow many people perceive it as a too technical problem or something which is driven from outside. I mean, just my personal point of view. And so let's look at some definitions so that we try to define, put the problem in a clearer form. So when we talk about the climate system, we usually refer to as the union of 4 domains and 4 interconnected subsystems: the atmosphere, hydrosphere, cryosphere, and the biosphere. And then there are many others. This depends on the time scale we are interested in. So we have some macroscopic driving and modulating agents: solar radiation, gravity, rotation, and of course we have many degrees of freedom, and we have, as pretty obvious, sensitive dependence on initial conditions. And so, okay, that's just to give some element. And now I would like to list a few things that I find it relevant. So somehow 3 just major challenges, theoretical challenges you look in the climate system. So first, just in a very simple point of view, is that it's a nonlinear system, and the stability properties of the mean state do not, in principle, tell us much about the full nonlinear properties. This is obvious in principle, but as we know, many linear wave theory and linear stability theories are constructed exactly on time means and some base state which is defined through means. So there is a problem that we know this theory will not be enough. There is no way to close the problem. On the other side, we have a problem that it's a system where the application of the fluctuation dissipation theorem we will discuss, it's far from being trivial. There's been a lot of attempts, and we'll discuss this hopefully in the future during the program, and others will as well. And the third problem is, since it's a multi-scale system, it's a stiff problem numerically, and we don't know what is the optimal resolution. So we have to play. We have a fundamental part of the problem is to look at parametrizations, and we know that if there is one thing we know is that from this is that the brute force approach, that is just putting more, just using bigger and bigger computers, will not give us the answer in some sense. And then there are problems which are experimental, which are just as big. So we have the problem of asynchronic coherence of data. So data don't have the same standard of quality, and they change in time. What is a rain gauge has changed in time many times, the official definition, and it's far from trivial to compare results. And also same, this is the diachronic coherence of data. Synchronic coherence of data, at the same time we have data of very different quality. It's not easy to merge them. And we have methods which are to merge this data even with models, the sub-data simulation and reanalysis that Sean mentioned today, but this is far from trivial. We have a lot of assumptions in doing this. And of course, basic problem. Another problem is the space-time coverage. If we wanted to have a good description, we expect to have in mind something which is more or less homogeneous, but of course, the data density is very different today between Germany and Antarctica, and surely we have data only since Galileo's time at best. I think the longest time series we have in terms of pressure is from the University of Padova, I think, and it's 100 years after Galileo. And the longest climate measurement we have is the Nile, is the height of the Nile. That's since about 2,000 years ago. So that's, which is impressive in fact, but it's not necessarily that much. This is pretty unusual with respect to many other fields.
Well, why do you qualify it as unusual if I think about evolution in biology?
Sorry?
If I think about
evolution, yeah.
Evolution in biology,
yes.
Or what geologists and geophysicists
yes.
and astrophysics
yes.
do, then actually...
Yes, that's good. You're right. No, this is, sorry, you're right.
Circumstances even worse, I would say.
I was thinking, you're very right.
I agree that with engineering science it is...
No, but many physics, I had mostly mind physical sciences, in fact. You're very right in this comment.
Science is bigger.
No, you're very much... sorry, this was typical science, whereby I meant what can be treated using the usual method, where you have an experimental apparatus, repeatable experiments. This is what I meant as typical science, to be clear. Then there are other fields.
That's not very typical in those fields I mentioned. That's not very typical in a lot of fields.
No, it's in a lot of fields, but like the construction of science, for the most part, is done in cases where you have things under control, let's put it this way. One can discuss a lot on the great changes in scientific method, which come, in fact, from, there are many, of course, the motion of the continents, evolution theory. These are required entirely different methods. The mindset to be defined as science, not by chance. But this is a similar problem, but you're very right. Thank you.
I'll just make a comment also, because you're quite right, there's a difference between instrumental data and then proxy data.
Yes.
But part of the problem is that proxy data is considered as a poor thermometer, for instance. That's isotope ratio.
It's a different observable.
This is temperature, but can't trust it too much, or there's, But actually, if you took a different viewpoint, you could say that this is a well-defined signal of past conditions.
But it's true.
You can analyze the data to understand its properties.
This is true. On the other side, you know that it degrades. So if we have data on sedimentation, there is a diffusion in time, so the precision goes down. So it's not the trivial situation. Let's put it, not trivial, the typical situation. Then there are many other, there are various things one has to, you have to take assumptions on this. Anyway, now I go back exactly, I had prepared this already. So the same graph that, exactly the same, so we stole it from the same website, and so I knew it as Smagorinsky's graph, but it's the same idea. So we already had discussion this morning about this, but I want to add something with respect to what Sean said. In fact, we have two things. So we have scales and scaling. That's first from the point of view of Sean, but we have surely features. Something appearing with the relationship between spatial and temporal scale. This is out of question. But you see, I like to see the social side of science. We invented names for these things, which means that these things are distinguishable to a smart human observer since the Egyptians' time, at least. So we know the difference. We have name for cyclone and name for a front, and we have actually the Mayans have name for hurricane as a feature. So that is, there are distinctions between these things. So there is a comparison of scaling and special features of special physical processes occurring at specific scale. And in fact, I found this simple, I'm impressed with this simple categorization of people look at, I'm here focusing on the atmosphere, but same can be said about the ocean. There are three tribes of scientists, sometimes mixed. Those who like maps, and they look for features, particles, cyclones, say. Those who like regularity, and they look for waves. They always want to find waves. Then there are those who like reversibility and look for turbulence everywhere, okay? And, being, having worked in Reading and continue to work in Reading, it's been very interesting to see these things very clearly. So just to give a schematic view. So about the features particles, so the focus is on certain structures which have a complexity per se. They are really rich, the dynamics is very rich. The best example, I think, is hurricanes. So studying the hurricane per se, it's a huge thing, it's very difficult, and but it's just a small piece if you want of the whole climate. And then you can study its physics, or you can study its trajectory, and these are actually extremely difficult games. We don't have a comprehensive theory of something like that. We have various, there are, of course, there's been very important contributions, but this is per se still an open problem, I think. And then, of course, we have turbulent cascade we've seen today, and I took a random graph without any special reason, but yeah, something I wanted to note, it was already discussed today, that there is nothing in the two-dimensional in the atmosphere. The atmosphere is a very three-dimensional object because of the interaction between the dynamics and the thermodynamics. That's exactly the point. Anyway, there is endless discussion about where the scaling is, the turbulence is quasi-two-dimensional, is quasi-three-dimensional, where are the interaction, where is the energy is injected, and so on. It's a very long discussion here. And then finally we have the waves, and these are so-called Rossby waves. This is one of the great joys, I would say, of classical meteorology. And these waves are very important for an enormous amount of things, including especially weather prediction, in fact. But what we understand is that these three pictures are partly overlapping, partly complementary. I don't think any of these tells the whole story. So just about going again into waves, if you do a spatial temporal expansion of waves of a field along the zonal direction, this is the geopotential height of 500 hectopascal, which is the height at which the pressure is 500 hectopascal in the mid-latitudes. And let's forget about the details. Look at this. These are you can separate between the waves that travel east-west or are standing. Let's look at the west-eastward propagating waves. And as you will see, this is omega, this is k. We see something which, of course, has a sort of a dispersion relation. The omega and the k is positive, so things go, in fact, eastward. But look, we have a huge spectral broadening. So why? Because, in fact, these are not really waves. These are things that grow, oscillate, and die. And the lifetime is more or less the same as the period. So they are waves growing and dying on a random background flow. So it's not obvious to treat them as waves, as simple waves. Okay, and if you repeat this experiment on some of the main climate models, you will see a portrait. Each model has there's a wave climatology of this climate model, and we see, I don't know, some models who have very strong low frequency variability, and some models who don't have almost low frequency variability. And we have differences. So we see that the representation of the properties of waves in a very simple diagnostic setting is far from being a trivial matter, even today. It's very far from being. And okay, so that's a first element I wanted to give. Now, I would like to give some idea of some properties of climate models, and we will discuss and see much more, of course, in the next days. But just for those who might be not so familiar. So when we talk about climate models, and actually when we talk about climate, if you look at what people meant by climate in the 70s is entirely different from what is meant today. In the 70s, there is of course a correspondence between what was the climate model and what people meant as climate, in fact. So in the mid-70s, by climate, mostly people meant the atmospheric properties, in fact. And then, of course, and then things have changed, and the models, of course, accordingly have changed. So what is a climate model? It's not just a matter of computation, it's a matter of concept. So if once people were, the state-of-the-art climate model would include precipitation and radiative transfer, then things have changed, including land. So a non-trivial description of land surface, a description of ice, then a coupling between atmosphere and ocean, where the ocean was not a dynamic body, but was mostly something that had basically a thermodynamic role. And then the ocean became dynamic, and the new components were put in the atmosphere. Activity was put in the atmosphere. Then we have the carbon cycle, we have vegetation, and we have the chemistry of the atmosphere. And things are changing furthermore. This is the fourth assessment report. In the new assessment report, the fifth assessment report of IPCC, which has just come out, things are even more complex. So we see these are, and interestingly, at each of this time, these models were among the most complex computer codes in the world. So that is, and this has always been since the 50s. So yeah, this is an image of one of the, it's not even ultra recent, but that's how a climate model looks like. So you have basically grid, can be grids, finite, can be grids or can be spectral decomposition, and basically, and you have a discretized representation of the geophysical fluids and a description of the interfaces. And this is very, very important and very critical. And okay, and so as you can see from this picture, what you have is that many things happen below the scales that the model is able to resolve explicitly. So, and this is exactly what is called for what is needed then to complement, to put some additional information in the model. And this is again one grand challenge that we are facing let's say, especially in these times. So again, to specify what are the goals of modeling, this is just using simple Lorentz 63. So we can have on one side studying the evolution of the properties, a local evolution of the properties in the phase space, and this has to do with the weather forecast. And on the other side, we want to be able to represent well the statistical properties of our system, and maybe their changes with some modulation of the parameter. This is the climate modeling part. And what people are trying, and I mentioned yesterday, we mentioned yesterday in the discussion, is to basically have models which are able to encompass all these things. Okay, so that's, and this is the so-called seamless prediction. Yes.
Isn't that mindset that really what I was calling weather and macro weather, because you have the idea that you have an invariant measure, and in actual fact, the climate is really the slow change of that.
Okay, no, that is, yeah, this is for given value of the parameters. In fact, if you talk about climate, that's, okay, that's a modeling of the present climate. If you want to talk about climate dynamics or prediction of climate change, then you have to modulate this thing with something. Yeah. Okay, that's, you're right. I mean, that's a good, it's a good point. And when we talk about uncertainties in climate models, we have, there's been a classification already due to Lorentz about uncertainties of the first kind, which are related to the initial conditions, and these are relevant, of course, especially for numerical weather prediction, but they are very important. In fact, not so directly relevant for climate models, but they are crucial to, we use different initial conditions to populate the attractor if we do an ensemble simulation. And then there is uncertainties of the second kind. Are we able to represent well the processes? And if we have the right model, are the parameters we put in our models correct? So is it a problem of structural uncertainty, problem of parametric uncertainty? And the last thing that I would add is the uncertainty in the metrics. That is, we have, of course, we have to choose some some benchmarks, some ways to compare model with model or model with observations. Are we using meaningful observables, or are we using observables that are not so relevant? That's maybe observables that are useful for us, but not necessarily relevant for the dynamics of the model. That's again, this is non-trivial, I think, a non-trivial issue. Now, something that results from this is that when we talk about when we construct a model for climate problems, we are in the case where always we need a plurality of models. That is, it is not obvious that at all, and that the biggest and most, let's say, the model that most accurately represents the world, as far as we know it, is the best tool to study every problem. So this is extremely different from, again, many other cases. If very often, if we want to study properties that take place on the very long time scale, it's not only a matter that the best, let's say, the best model we have to do short-term climate prediction are unfeasible to use because they would be too computationally expensive. This is usually the argument. It's not so. Those models will probably do a much worse game than other models because they are tuned, they are prepared to simulate well our climate, not climates which are very different from ours. So again, we have to select different tools for different problems. Interestingly, so if you use a sort of a very conservative point of view, all models are wrong because they are not able to represent perfectly things, and not even necessarily well for all the. But of course, we are not blind. We have tools. We have, in fact, these tools. These models are very important. Okay, and just to give you a sense, if I take maybe one of the best climate models we have, or climate modeling suite like ECHAM, developed MPI in Germany, this is like a huge code which is extremely good at simulating the climate. Our climate and climate change in the neighborhood of this climate. But the problem is that it's a bit like an oil tanker in the sense that it's extremely a fantastic tool for performing one or some tasks, in this case metaphorically to transport oil. But if I have to navigate around the Greek islands, it's not a good tool. Okay, we need something which is faster, which of course is not as good in transporting the oil, but it's good for a different task. So simpler model can be very good to approach, to study problem as an example of very long time scale of paleoclimate, tipping points and so on. So again, this is just to say that we need a plurality of approaches. Now, I will skip this and just say, okay, let's now go a little bit after this, I think, useful or necessary excursion on what is some aspects of climate science. So let's try to look at what are, we want to talk about the thermodynamics, at least introduce it. So let's look at the energy fluxes. So basically what drives the climate dynamics is the so-called differential heating. So we have the system, different parts of the system absorbs radiation, solar radiation, and this creates gradients of temperature and of chemical potential. So the system is a non-equilibrium system, which, when the parameters are fixed, is at steady state. So of course, the first very important, let's say, differentiating process, the thing that drives the system out of equilibrium, is that most of the incoming radiation is absorbed in the lower strata of the atmosphere. So that's the first thing. So it's the system, the atmosphere is a system heated from below. That's very important. So of course, this makes it a little unstable. Okay, so we can have instability like convection. The ocean is a system which is heated from above. So it's a system which, by definition, will tend to be much more stable. Then there are other processes related to salinity, but that's another story. And then the other very important differentiation in heating is due to the fact that we have, of course, a differential heating between the tropical and extratropical region, And if we observe from space, we have that, around 35 north, 35 south, we have that in this region, we have a surplus of energy at the top of the atmosphere, of energy budget at the top of the atmosphere, and we have a deficit poleward of this. And of course, it's already, I like this graph because it already tells you a lot. With a little bit of thermodynamics and concept of steady state, we must have a mechanism by which this surplus is transferred here. If we observe a planet, and we know nothing about this planet, and we observe a differential budget of energy, we must infer the existence of a mechanism that transports energy. So this is a very general, in fact, property. And okay, so this is the other mechanism, the other aspect. So an important thing is that we will see the geophysical fluids do basically perform this job of transporting heat, and so they reduce the temperature differences that we would have between equator and pole in the absence of this mechanism. On the other side, where does all the difficulties we have described before come from? They come from the fact that the intensity of this circulation, both oceanic and atmospheric, results exactly from the presence of a temperature difference. So these flows kill the available potential energy that generates them. And if we manage to close the problem, we would have a closed theory of climate dynamics, which we still don't have. Okay, so that's a very general issue. Okay, now let's try to look at, again, let's using some concept of thermodynamics, let's try to see some properties of the climate system and of the models. So let's assume I do this thought experiment. So I have my climate system. So basically I want to study a general problem of climate change. So I am in a regime that Sean would call I'm in a macro weather. So I have fixed parameters of my system. And this is, I plot on the top, on the y, the integrated radiative balance at the top of the atmosphere. So this quantity will fluctuate around 0, just by definition that the system, which has been prepared at t minus infinity, is at steady state. Okay? Then at a certain point, what I do is something happens. As an example, we change the opacity of the atmosphere by changing its composition with CO2, or we have a change in the irradiance from incoming radiation from the sun for a certain period of time, which is indicated in red. And as an example, let's say, like in the case of increase in CO2, this creates a positive imbalance in the radiative budget at the top of the atmosphere. So basically, let's say this is a forcing we observe. And then let's say that when we reach at this time T1, let's call it T1, this is time T2, the parameters are set, fixed at the new value, and they are kept constant. So what we should have is that no matter what, this system will slowly, of course there will be fluctuations superimposed, I just remove them, will slowly, or not so slowly, depends, anyway it will relax again towards 0, because it will reach a new steady state. So this will be a new non-equilibrium steady state at times plus infinity, or in practical terms, for a time much longer than the slowest time scale of the system. And of course, this integral is just the total warming. It's very simple. It's just physical. This is, to me, the easiest way to say how much heat is stored in the transient inside the system. Okay. So we go from a non-equilibrium steady state, transient, a new non-equilibrium steady state. This applies not only to the whole climate system, but to any subdomains of the system, just by using steady state. So just by using a concept like Ness, we are able to frame the problem, I think, more elegantly. Now, as an example, in the case of the atmosphere, tau is very small, so you will not see much of this. Now, let's see how one of the leading climate models of the current generation behaves. In fact, what we have found, to our shock, is that most of this model, that we will plot the run in a second, has a bias in the steady state, then it responds as it should to a change in CO2, and then there is a relaxation, but it's not very clear whether it's going to relax to the same bias or to a new bias. So again, the presence of a bias creates a lot of conceptual problem, and let's see the run so that I hopefully convince you. And this is the bias of our typical 0.5 watts per square meter. This is an IPCC experiment of 1% increase of CO2 till doubling, which is around here, and then this is the relaxation. Okay, that starts, and it will take about 1,000 years because it's a model with an active ocean, so it has a slow.
No, it's actually a power law.
What?
Convergence. It's a very, very slow power law.
Well, depends.
They exploded about minus 0.1 or something.
Okay, I didn't study that range, so
it practically does. For all practical purposes, it won't converge. It's too slow. I mean, it does, but it's just so slow.
Yeah, I don't know. I never looked at it. It's probably right. Just to say, anyway, this is. My focus was on the fact that we have this bias. So, as an example, this tells me it doesn't give a simple rule on how to estimate the real change. And look that the bias, it's of the same order of magnitude of the forcing we get. So it's a problem, I think.
Maybe there's a specific physical reason for why could we have multiple steady states if this forcing would put you in a different well?
No, this is not, look, that's the point. This is the only one, not the only, but the good observable such that at steady state it has to be 0, regardless of the final state you get, because it's the energy budget at the top of the atmosphere. So even if you go, say, from say you do a huge forcing, and you go to a snowball state, so it will plunge down, but then it has to go back to 0. There is no way, because it has to be a steady state at the end. So that's why I chose this observable. I don't have the skill, I have an absolute measure of the skill. It has to be near 0, no matter the final state. Then the problem of transition is another issue. But this works also for the transition, but it's actually a very important point. So, we go now again to our comments. So before, well, we care about temperature and precipitation, not about energy. Sounds a little problematic after what we've seen. And, let's look at this last comment, which is not provocative, it's just a comment. So in many physical sciences, if we make a model and the energy is not well treated, people will not be happy, will not publish, will not get published. And yeah, in a model like this, we get thousands of publications, hundreds of PhDs. Okay? And the people who do this are very smart people. So it's a different way of looking at the problem. We have to think about this. I find it conceptually very intriguing.
So Valerio,
yeah?
In your previous slide then, do you know where that energy is going in the controller?
Yes, I will discuss this in a second. That's exactly. So in fact, today I put part 1 on the thermodynamics because I want to talk about energy budgets. Very simple. The very simple part, energy budgets. The boring energy budget, and we will see that there is a lot to learn from there. And then, hopefully, next time I will talk about other processes. This is just energy budget. So I think we have to get energetics right and understand it before going to more complex properties. So just to say, already this is non-trivial, and we will see a couple of things that explain this. Okay, so now this was one model, and now what we did is repeating the same for all the climate models included in the 4th assessment report of IPCC. So these are 20 climate models that have been used. I mean, they are state of the art, were state of the art in the mid 2000s, and actually we have now repeated experiments for the new models, and the results are about the same. So I show that, and I will leave you. We will comment on this. So these are 20 models, and we have a pre-industrial control run, which is a steady state, and then we have one of the forcing runs used by IPCC to study the change in climate in the future. So this is pre-industrial energy budget at the top of the atmosphere, and this is 0. The 0 is scarce. So all the models basically are positive. So meaning all the models have a positive bias. So they have more input of energy than output. Okay? It's not, they are not, this is interesting, they're not distributed around zero.
Average of 100-year run.
Yes, and this is extremely, you see the error bar, very small. So, okay, that's the first that I was shocked, I was found interesting. The sign, the presence of a bias, and the fact that most models, except this, are positive.
Because they discovered just I think in 2011 that they had misestimated the solar top of the atmosphere solar insolation by about 5 watts.
No, but the problem here, this is from the model. This is not what the data you use. So that it's a matter of consistency. It's not a matter of realism. That's exactly the point.
All right.
So, and this is the variability, which is different, but let's consider just the x-axis. So this is the mean. This is a huge number, just to give you a sense. This is the same size of very strong climate force. Okay, 1 volts. Some of these are 4, 3, 7. Okay, these are big numbers. Now, of course, the issue is, okay, there is an error, but all the energy is going to be stored into the ocean. Since the ocean has a huge heat capacity, who cares? It's going to change by 1,000th of degree the temperature of the ocean. Who cares? So we decided to do the analysis separately for the various components. And in fact, look at the atmosphere, and we have negative biases here, and we have some of these huge biases. This would mean a bias of this size means the atmosphere would warm by 1 degree per year. Of course, in all these models, the climate is very stable. So we have there is a problem. This energy enters and something happens. What does it happen? And that was very non-clear for us. So now, again, we have some models which are close to 0. Still, even half a watt is a lot for the atmosphere. You would get like this might be okay. Some are negative, which is quite strange. And in the case of the ocean, in fact, the bias is comparable to the bias of the atmosphere. So the problem is a structural problem. It's not a problem that we are storing it somewhere, which is it's not a transient problem. It's a steady state problem. It's extremely different. Okay? And we have another interesting case where we have the emergence of a problem is on land. Okay, which is again a thin system, a system with very small heat capacity. So the problem occurs at interfaces, must occur at interfaces, has nothing to do with the heat capacity of the system. So this is the identikit we found. Okay. Now, another thing you can find is, let's say this is a little messy, but in a second, if I force the system with the CO2 push, all the models will move towards the positive range because they respond in the right direction, and then they relax as they should, and this is fine. The question is, what is missing? So, what is the process? And the process are two main processes. One is that the dissipation of kinetic energy that is described by some viscosity-like process and in various parameterization is usually not injected or not perfectly injected as thermal energy at the bottom of the cascade. So if I dissipate kinetic energy, at the end, at a certain point, this must become heat. There is no way. If you don't put it in the system, you have some sort of black hole of energy. Another part of the model where this problem applies comes, in fact, if you look at the hydrological cycle, and you look that in some models have a discrepancy between how much water hits the ground and on the average how much water comes out of the ground. And this is not a problem of storage. If you lose mass or create mass of water, if you multiply this by the latent heat, you change the energetics of the system a lot. And this creates a bias again. So what happens is that this energy, this is what is creating these biases. which are actually not so small. Interestingly, what does the system do? So let's think the system needs to, is losing energy on the average. That's what we have found. So in order to be a steady state, it has to emit less than it receives. So there are two ways to emit less than you receive. Either you increase the albedo, that is, you put more clouds, it reflects more radiation than it should, or you decrease the temperature a little bit, so that you emit less long-wave radiation. And the cold bias of climate model, it's been always a standing problem. People have found since the 70s, and they think this is the reason. So the system gets slightly colder, so that it emits slightly less radiation, and then it takes care of the ghost energy that is lost. So it's again just using, and you see the same problem if you look at the hydrological cycle. So that you integrate. Okay, so again, now we now looked up to now at the total energy. So this is the energy integrated globally. Now let's look at still in the energetics, but in the energy transports. So as we said, the presence of a surplus and of a deficit implies, and the steady state condition implies that there is something, some monster, something transporting energy from here to there and from here to here. Okay, so it's actually not very hard to, just using the simple fluid dynamic equation, to relate. Basically, you write a conservation equation for the total energy of the system. You have a flux, transport, and you have a convergence of fluxes, turbulent fluxes and radiative fluxes. So if you take long-term averages and integrate, you can basically relate the fluxes at the top of the atmosphere and at surface due to radiation, latent heat, and sensible heat to the meridional gradient of the transport. It's just a simple, it's literally a problem. It's a divergence problem. It's nothing special. But again, looking at fluxes, we reconstruct the averages of 3D plus 1D flows. So I like this idea. It's a constraint we find. Okay, that is not very relevant, but this is what we get. So each line is one climate model. So let's try to see the good and the bad. So the T is the total transport, red is the atmospheric transport, and O is the oceanic energy transport. Enthalpy, in fact, enthalpy transport, to be precise. So look, all models peak exactly in the same location. So the peak is represented for the total transport perfectly. And there is an old paper of Peterstone that explains why one should expect this. It's a very strong constraint due to the geometry. And the models, in fact, respect this very well. But look, there is a range in the amplitude of the transport. So this is the second, if you want, largest, the second largest scale energetic property of the system. What is, how much energy are we transporting? And the differences is of the order of 20, the range among models is of the order of 20%, which is not far from being small, and means there is still a lot to learn. And we see that the atmospheric, again, the position of the peak of the atmospheric transport is the same for all models. Look here. But still, the range is 20%. And if instead, if we go to the ocean, the peak, this is the atmospheric peak, this is the oceanic peak. And the oceanic peak, of course, has much more uncertainties. And the relative error is order of 50%. Interestingly, the world looks extremely more symmetric than the topography and the position of continents would suggest. Because when we look at these large-scale properties, the system is extremely good at forgetting what happens, the details. So that's a very strong property we have. Now, I just wanted to, these plots, just to give you some sense of the agreement of disagreement. So this is a max peak of the transport measured through the energy fluxes at the top of the atmosphere. And here you see, this is between 5 and 6.5 petawatts of average transport. And this is the range of the models. Look, some models, in fact, are quite different, just a couple. Now, if we look at the atmosphere, again, I just wanted to show the range between about 4 and 5. These are big differences, and it's huge. It's a challenge to understand why these models are so different, and it's not trivial. This is, we would expect that in such a property should be very well captured, maybe within few percent by this model. This is a very large-scale property, but it's far from trivial. And in the case of the ocean, we see that the spread is even larger. Interestingly, there is a bimodal structure in the case of the ocean on the peak of the transport. So some models see the peak of the transport at around 17 north and others around 24, which is literally a different location. So again, why? We don't know. But these are big challenges we still want to understand. And then we're going towards the end. And just to show you, so this is the same figure I showed you before of the peak of the transport. And now I show you how things will change, are projected to change with climate change. So this is again what we have. So this is how, this is the previous graph I showed you, and this is the impact of climate change. So we will have, you see, systematic increase, in fact, of the transports. And this is mostly due to changes in latent heat transports. Okay? So because this is interestingly, warmer means typically that we have more moisture in the atmosphere, and this will be transported, and so this will preferentially warm up the high latitudes more than the low latitudes. So this is one of the reasons why the northern latitudes will warm relatively more. Okay? And yeah.
It looked like the ocean was transporting less, though.
Yes, the ocean. Yeah, the ocean. It's in. You see, in the north, no. In the south, yes. But you see, really here there is a huge uncertainty. Look, here for some models you have counter transport.
It's going backwards.
Yes, you have transport towards the equator. So there is a lot of uncertainty. That's why it's very difficult. The problem of ocean, the heat transport of the ocean near the equator is extremely non-trivial. I mean, El Niño and all these things are partly in there. So anyway, you see that the change in the atmospheric transport is positive both in the south and in the northern hemisphere. It's very, quite correlated. And, no, this is not interesting. Yes, that's interesting. So if you look at the correlation between the transports, the variability of the transport of the atmosphere and of the ocean in time, you get a negative correlation. So if in 1 year the atmosphere transports more, the ocean transports less, and vice versa, typically. How is this mechanism of compensation? We don't know. We don't know. We really don't know. I mean, we have, of course, ideas, concept of why, but mostly it's hand-waving. We have simulations to confirm this. I mean, this is to me a fundamental problem that is far from trivial. Okay, so there are these so-called compensating mechanisms. And okay, now concluding, I just wanted to see. I'm using, as often sometimes in my presentation, a very nice figure of a colleague, Mr. Clydon from Iena, who's basically has put in this scheme all the multi-scale and complexity of the Earth, explaining that when we talk about climate system, we have, basically, if you go towards the center, we go towards longer and longer time scale. We have coupling between processes, coupling between time scales, and we have gradients that, in a very nonlinear way, very far from being a Onsager kind of relationship, drive fluxes. So it's extremely far from a quasi-equilibrium picture, and we have a coupling across scale in the fluid part, which is basically here, the red, and then we have, through the biogeochemical cycles and, in fact, the biotic activity, all the way to the crustal properties. Interestingly, you find coupling between the fluids and the crustal and basically the solid Earth when you study the conservation of momentum, of angular momentum in the atmosphere, because fluctuation in the intensity of the winds are related to fluctuations in the length of the day, and this is measured very precisely. So that's so somehow to go forward. Yeah, I think one can use methods of non-equilibrium statistical mechanics and thermodynamics to study macroscopic properties of the system and to talk about climate change. And it's something I would like to talk about later in the program. And in fact, one can construct a thermodynamic theory which relates basically gradients in heating rates into generation of organized motion, extending some of the result of Ed Lorentz. So yeah, just to conclude, so somehow I hope I convinced you there are many challenges that are related to the climate science and to climate modeling that are just starting to unravel, and there is a lot of interesting stuff even on the very basic properties, large-scale properties of the system, and we have to develop some smart techniques to new ideas to study this. And something that is important, I hope I convinced you, that just expanding our computing abilities without knowing which questions to ask can lead us astray, in fact. Because, interestingly, some extremely complex and extremely expensive models are not able to represent energy budgets. This is, I think, the first signal. And if you look at momentum budgets, it's worse. It's much worse. So we have models that generate angular momentum and models that destroy angular momentum. And unless you conjecture the existence of a divinity that stores this, it's a problem. Okay? And next time I hope to talk about entropy, efficiency, and how we can use macroscopic thermodynamics to study tipping points. Okay, I conclude here. Thank you very much. Yes?
Looking through the literature and whatnot, I found there's very little study done about the statistical properties of climate models. I mean, Klaus, Frederick, and a few people have looked at some spectral properties.
Yes.
But actually, very little. I mean, they don't really know, and so there's a lot of interesting things that can be discovered, including you can look at, for instance, since many of them have ensembles, so you can look at with identical boundary conditions. How do they converge to their climate?
Yes.
And you could compare this to data and whatnot. And the interesting.
No, but yes.
Well, I'll just finish because the interesting thing there is that they converge, but very slowly. The models converge to their climate, but extremely slowly. But they don't. If you compare them to reality, they don't converge to the same climate. But if you look at the anomalies, the difference between the states and the state after a long integration, that the statistics are very, very similar to those you observe. So the fluctuation statistics at different space scales and time scales are very similar, but the convergence to the actual climate is not. I mean, they don't converge exactly to the right climate. So anyway, but
yes. No, I mean what I can say is that surely what we need to look at. Let's face the truth. I mean, on the average, usually the climate model are tested and tuned by looking at certain observable, which can be tropical precipitation, average surface temperature, and this and that, which are very important. But it's clear that as soon as we look at variables which are relevant, physically relevant, without questions, because if you look at the agreement of these models on, say, surface temperature, it's infinitely better than this. Immediately, they are totally far away. And this is a big problem, because these models will respond differently to climate change. They have a 20% different energy transport. It's a lot. So, and even more if you look at then fluctuations. I mean, another problem that is in this direction that I find relevant, and it's at the center of the literature in these days, is about extremes, just to look at certain properties. So one problem is we look at extremes, we have extremes in data, in say in observations. These are point time series. If I have a model which gives me output on a grid, I can study the extremes in a grid point. How do I relate the extreme in this gridding with the extremes in this other gridding? It's far from trivial. The theory of a spatially extended extreme is extremely difficult, and if any at all exists really. How do I create a remapping of data among grids when I look at properties which are not averages? This is very tricky again. And how do I do extrapolation or interpolation of this property? So, and in order to do this regularly, if you need some structure functions, and you will need to study the properties you mentioned very accurately. So I think learning the spatio-temporal properties of these as random fields is what you need to do upscaling and downscaling. I mean, to do the downscaling and the parameterization is clear, but also to upscale. This is very important because you can have large fluctuations that you don't see. I don't know.
Can you go 2 slides back?
Yes.
I think it was 2 slides.
Yeah.
No, it was the one where you had 4, probably one more.
Yes. Yeah, of course. This?
Yes, yeah, that one. So you make that point about stochastic forcing ad hoc closure theory for noise. What? I mean, that's probably not. I had yesterday a thought that might relate to it, but only to forcing that. People do closure theories.
Yeah, but yeah.
And wait, very complicated.
Yes.
But now it seems to what you see now emerge, I mean, understandably, is that people use noise to close off the scale, time, or space, which they don't know.
Yeah, of course, yes.
So it's used in essence as some kind of closure.
Yes.
One of the things which is not clear to me is what is the link between, say, the more old-fashioned closure theory, whether or not they worked,
yes,
leave it aside, and there's putting noise in as an ad hoc closure. Because I would think, the simple viewpoint is that we know the equation of motion. When we don't understand them fully, we know them. Then you would think that you could constrain the noise more given that knowledge. That there seems to be a huge gap.
Yes.
And that was, after discussion yesterday, a topic which might be hidden in the topics which you put up yesterday. Now, how that relates to your remark there,
the remark, it's thanks. It's this is what you're asking is a very central problem, and I mentioned at the beginning. And saying that this problem of closure is just a technical detail is very wrong, because no matter how low we go with resolution, there will be a lot that we are not able to represent. So this is a fundamental problem, and is related to the presence of variability at all scales. This is out of question, so it's crucial. So traditionally people used to put parameterization, which are closures, so you want to represent the average effect of small scale processes on the large scale variable as a deterministic function. This was the tradition, and this is mostly used as of now. Then, let's say in the last 10 years, people have more, people knew this in the meteorology. Of course, this problem is known in the physical literature since the 60s, at least the Moritz Fanzig approach. So the problem is that if I have a two-level system and I want to construct, I want to study the evolution only of the coarse-grained variables, the rest will appear as a deterministic correction, a stochastic correction, and a memory effect, in fact.
Yeah,
so,
but my question is, there seems to be a huge gap between the two approaches, and somehow...
No, but let me finish. Yeah, no, in the sense, this is what the question is, you can even develop the theory for this, for the geophysical setting, and during the workshop, Jeroen Wouters will talk about this, in fact. And one thing is constructing then this projection operator for a system of that complexity. So of course you have to create a balance. Okay, so I think it's important to frame the theory well. The idea of adding noise is crucial. It's a very good idea, out of question. Paul in front of you is one of the leading experts on this, so he will surely discuss this. it's tomorrow we can actually it's good to discuss. And how to do this, it's far, you can have a more or less empirical approaches. You have empirical mode reduction, you have approaches, you have averaging theory, you have various things due to MIDA, you have empirical stuff, and they all boil down to trying to do this accurately. I think you can, in fact, construct using both response theory and Moritz-Manzig, in principle, the right parameterization. But it's far from trivial implementing it, and this is a crucial thing. So we cannot neglect this aspect. But yes, there is another aspect. In fact, the small scale things are inherently irreversible and contribute to entropy production. One of the ways to constrain is to study how entropy production changes with scales. That's another thing again. You can use again macroscopic properties. But yeah, this is a big open question. I mean, that's one of the reasons why we are doing this program, to discuss this fact, in fact, and how to, and yeah.
So, what's the climate sensitivity in terms of thermodynamics?
What do you mean?
Climate sensitivity.
Yeah.
Well, in your theory, what is it? How you?
It's not a theory. I didn't produce, and unfortunately, here don't.
It can be like a question for the next time.
I mean, like the problem is okay. Climate sensitivity. Okay. I define as climate sensitivity the static response of the system to any sort of perturbation, a general climate sensitivity. Climate sensitivity is usually intended as how mean average temperature change with respect to a doubling of CO2. I mean, you do not just, the answer is the question itself. So it will depend on a lot of things. You can compute it, and you could give an answer accurate enough in principle as much as you want if you are able to study the response of the system. You can write the operators that allow you to study this property, and we have just, I hope to present Friday during the workshop this result, so that you can predict climate sensitivities from other properties. But that is a totally different ballpark. So here you have to use some methods of statistical mechanics, not this. This is consider all of you seen today as a diagnostic of climate energy budgets. That's it. It's not more and not less, and it's not refined. These are very simple budgets, Gauss theorem once or twice, and that's it. But just to say that these problems are very present today in the modeling. So there is no much theory, in fact, here that I am doing. This is really an introduction to the problem, at least from my point of view. Sean?
Yeah, maybe let's go back to that Stommel diagram.
Yeah.
Stommel, Smolinsky.
Yeah.
Anyway, so it's just. Yeah, I admit I went very quickly, but we have different viewpoints on that, and I thought it might be something obviously that should be sort of thought about and discussed. But the typical view is that you have different phenomenology, and because of phenomenology, you assume that the dynamics is different. So you have a different model for cycles.
No, yeah, that is, yeah.
But the fact is that if you have anisotropic scale invariance, so you have one dynamic, but the structures can be squashed and rotated and deformed differently in different scales, the aspect of morphologies can be totally different at different scales.
No.
Actual fact, the dynamics is the same. So it's a very dangerous thing to try and deduce the dynamics just from
No, wait, maybe I was not clear. What I say is, historically, we have models for this, models for this, models for this, model for this, and many others. So there are different set of equations, different set communities, and different approximations. But this is the manifestation of the dynamics of the atmosphere. So there is an underlying physics. So the fact is, we have on one side coupling between scales, we have specific phenomenologies that emerge, and the possibility of representing them approximately on their own, apart from boundary condition and fluxes, okay? In separating slow and fast things. So said, of course, the point is these things are connected. I'm not saying they are not connected.
But I don't think you can. That's the whole thing. You can't actually isolate them. That's the thing.
Oh no, I don't say I isolate. In the scientifically, historically, they have been isolated.
No.
And no, I'm not saying. Of course, I mean the whole problem is, if you want, you can see that even the things I discussed today mean in part the problems that occur at the smallest scale. That is, turbulent diffusion at the smallest scale of the model, hydrological cycle transfers, the smallest scale of the model, impact the largest temporal and the largest spatial scale in this case. So we have an upscale of, in a climate model, things are cut here, okay? So the fact that these parts are not parameterized or treated in a consistent way, not in a correct way, implies errors in the longest scale. So of course, you need to have a comprehensive view. It's not obvious. What I hope to talk about in the future is about how thermodynamics can help us to treat this. But immediately you see that the problem occurring at the smallest scale is not limited to the smallest scale. You find it by looking at the long-term average of energy budget at the top of the atmosphere. That is like the most global quantity you can have. So that is exactly the point. You have interaction across the scales. So if you miss the turbulent dissipation here, you're going to see it up there, and it's going to be a big number, 1 watt per square meter.
And then what they actually do with the models is they try and correct for this bias by, right? Is that how they?
Partly it's done
with ad hoc way.
ad hoc way. I mean, it's not all models are the same. Some models do it more accurately, some less accurately. But as an example, there are modeling practices that create troubles. As an example, say you have snow falling on the Rocky Mountains, and your model snows too much. So you start to accumulate 1 meter, 2 meter, 10 meters. You in principle you would create a glacier, but the models are not able to treat a glacier. So what many situations, what people do is that, I don't know, there is a rule. If the snow is more than 10 meters thick, the rest is destroyed. Okay, and the latent heat of this, the energy it took to evaporate this thing, have it snow there, all this energy difference is lost. And this, if it's systematic, it's a small number, but that's the same with dissipation of kinetic energy. If you do scale analysis, which means if you separate, it's small. It's nothing, but it's always positive because of the second law of thermodynamics. So it accumulates, and you're never going to get it. It's not a zero. It's not a zero mean effect, not even asymptotical. It's a positive definite quantity. At each instant, it's extremely small compared to the rest, but you're not going to get away from it. That's one of the things. Yes?
Yeah, I have a question regarding the diagram with relaxation.
Yes, please.
So does it mean that, did I understand it correctly, that the models actually do not respect energy balance?
Yes, you did.
So why doesn't one put there the requirement for them to respect energy balance?
You are asking the right person. I mean, we published with the, I can refer this. I mean, we published in the Reviews of Geophysics this article where we do this extensive analysis. And let's put it this way, we had not easy life. As an example, we were said, since I don't know the anonymous reviewer, but an anonymous reviewer told me, you don't have the right to publish this data because they give a bad image of the quality. Yeah, I have the image. I mean, it's, yeah, I mean, this is just a stupid statement, incredibly stupid statement. But, and many people, I mean, I had to think that this is, some people think it's relevant. To me,
That's the kind of stuff that gets scientists on the front page of newspapers looking really bad. Those kind of statements.
what the yes.
Let's not publish the bad data because it makes us.
But this was I mean, again, one has to interpret, okay? Because the fact that you have this bias doesn't mean that the model is worthless. That, I mean, to be clear, I put it in the slide. This does not mean the model is worthless or is not good at representing climate change. But it is an unnecessary mistake that we could cure because we know the equations. It's enough to transfer something or check. You know, it's an interesting thing is that in the one of the models used, the unified model used in Britain, there is a flag that you can select or not to implement whether the energy dissipation of kinetic energy enters the energy budget of the thermal energy, how it's called, of P. So you can even select not to do this. Why? I mean, like, why on earth would you want to do that? But it's something that is not obvious. Okay, and I think it's just a problem that you don't want to have. The problem is, it underlines that you can have mistakes at the level, small scale, that really can impact a lot of properties of the system. Remember that since the 1970s, the spread among climate models in their representation of the climate response to a given change in CO2 has not decreased. The spread among models. Is it? I mean, there is a problem. Of course, it's mostly related to clouds, yes. But is it possible that after 20, 30 years of development, you have 20% discrepancy in the large-scale energy transport and in the temperature response? I think this is a matter for thought. We should understand why, and we should work on this. I don't know. I'm not saying these models are good, are very good tools, are fundamental tools, but
is it clear that you should thermalize all the energy that your model dissipates? Because usually your dissipation scale which will be too high, that it's physically worth.
Yes.
So you need some sort of internal energy storage.
Yeah, but I mean, the question is, it's a matter of consistency, I think. So if your model ends at, but also on this aspect is very important. If your model ends at 100 kilometers, so this is the smallest time, spatial scale, horizontal spatial scale, and it has maybe 100 or 200 meters in the vertical, just to give you in this one. This is your smallest scale. So below that, it's what? Thermal energy, or what? Or you must put a model for what is not thermal energy and is not dynamics anymore. But anyway, you should have a zero sum in the energy at the end. So the easiest is just to put, I can tell you the example how we discovered this in the climate model we started to use in Hamburg, where it was easier to do this operation. So we tested this, and the model was out of the out of balance, let's say. So the energy budget and the average was different, was about 1.5 watts per square meter out of budget. Once we just did the simple operation of reinserting this energy, the bias went down by a factor of 10. So of course there is always, it's never zero because there are numerical uncertainty. I mean, let's not be, I mean, just pedantic. There will be mistakes and will be discrepancies, but just by changing this, immediately the system was, the thing was energetically consistent, more consistent by a factor of 10, which to me is enough. I mean, I'm not.
But you can still be wrong without getting the energy wrong.
Yes, you can be. No, it's all combination. I mean, you know, the point is that you cannot be right without the energy right, but you can be very wrong with the energy right. But if you don't have the energy right, I would be very uncomfortable. That's me, but that's me.
Huh.
But yeah, and then remember, there is the momentum. There are other things. An example which is related, the exchange of momentum at the surface or near the surface in the boundary layer, very difficult thing. Okay, now if you have you emit gravity waves, and these gravity waves go away. So if you have an error in the budget of momentum at surface, it's not going to impact much the surface. But you know, there are these gravity waves that take a lot of effort to be parameterized, that spit away this momentum, and it stops in the stratosphere. where there are, one molecule here and one molecule here, okay? The density is very much lower. Then this little it's a momentum. It's not velocity, so there is a rho times. So it's a budget of something which has a physical quantity. So if you have a small imbalance in related to a region of the atmosphere where you have high density, this thing is transported in a region where the density is much lower, the impact in terms of velocity will be much higher. So that's one of the reasons we have a great discrepancy, and I mean, Paul again is an expert on that, in the stratosphere, in the jet. And it's known, it's related to the problem of gravity waste, and I'm not a big expert, but this is one of the things. And it's clear that you can have effect far and very relevant, and then it's hard to fix it. Okay? So that's another example.
So other models where one basically throws away a couple of equations and puts in energy and momentum balance.
I'm sorry?
So other models where one throws away a couple of equations and puts in energy and momentum balance.
What do you mean to throws away the equation?
Well, I mean, basically the model, forget about throwing away equations. Just put in energy and momentum.
Yeah, there is as an example one of the model which is I think it's there is one of the models, not in this the newer data set, which would be like here, 0.
And how do they perform compared to?
It's in terms of, the problem is that's another aspect. Depends what you are interested in too. Because this is the first part of the story. I mean, let's say if we want to create a cascade of observables, how do we do? So we have to start somewhere. What I think is that we should start from energy, as an example. So this can be one. Then you can have the transports we have seen. We can have transports at various latitude. We can have transport of water. We have a lot of things which are large scale, which are absolutely crucial. As an example, I tell you because these things impact very much a lot of regional problems. So we have studied the hydrological cycle over, say, some big river basins. Okay, and you have that different. These are very big. I mean, I'm talking about Indus, Ganges. So some models don't. I mean, models disagree a lot on the convergence of water vapor in this region by a factor of 2 or even more. Okay, so if you have a model where there is a discrepancy in the water convergence over the Ganges by a factor of 2, and then you want to use this model, these two models, to study the risk of flood. You understand that the two models will give you entirely different answer. I don't know what is right. But again, it's large-scale properties that then impact something very, very, really, very, very important. And there are lots of issues in this. So I think there is a lot of room for researching these properties and for trying to improve. Then you have to understand why. This is just diagnostic. I'm not claiming I know the answer. I think we have learned the answer for certain things. The other aspect is clouds. If you look at the distribution of clouds, you have discrepancies, which of course will be related to the transports, because the meridional density of clouds will impact the meridional gradients of albedo and will change the radiative budget that are related to the transport. So these things then are coupled in an extremely difficult way. So it's not easy to understand what is wrong, but at least we want to see if there is a problem. Thank you. Okay. Shall we stop here? Thank you.